Hello everyone, this is Madhuri, working as Assistant Professor in the Department of Electrical and Electronics Engineering at MLR Institute of Technology, Hyderabad. Today we are going to discuss some numericals on the DC motors, as we have covered various topics of the DC motors like the torque equation, efficiency calculations, and we have also seen the demagnetizing and cross-magnetizing ampere turns in the armature reaction. So all these formulas or all these numerical expressions which we have calculated for the different topics of DC motors will be now applied on the numericals and will be studied for different kinds of numericals for different kinds of motors. So moving on to the first numerical, we see that a 4-pole DC motor takes an armature current of 6 amperes. So armature has 480 lap connected conductors. The flux per pole is given as 20 milliwebers. So now we are going to calculate the gross torque developed by the motor. So we know that is the equation for the torque which is developed across the armature, so which can be considered as the gross torque also. So now we are going to calculate the gross torque which is developed. So for this we require the flux per pole which is given in the question as 20 milliwebers. We got the poles as 4 which is also given in the question, and the number of conductors are 480 and the number of parallel paths. So the armature is lap connected. So for any lap connection we have the number of parallel paths will be equals to the number of poles, so which is nothing but equals to 4 now. And the armature current or the current which is taken by the armature of the motor is given as 6 amperes. So from the direct formula we can calculate the gross torque (20 milliwebers) multiplied by number of poles into the number of conductors as 480. Armature current is 6 amperes divided by number of parallel paths is again 4. So upon calculating this numerical, we are going to get the gross torque of the torque which is developed by the motor. So this is how we calculate the basic torque which is developed by the motor by using the direct expression of the torque equation from the torque equation of DC motor. Moving on to the next numerical. So we have a 200 volts, 2000 RPM, 10 amps separately excited DC motor. So separately excited DC motor. We have the separate excitation for the field winding and also the separate excitation for the motor armature. This is called as separately excited DC motor. It has the armature resistance as 2 ohms. Armature resistance is 2 ohms. And the armature current is given as two values of armature currents is given, 5 amperes and 10 amperes is applied to the armature and field windings of the motor. So if the now armature draws 5 amperes from the source, calculate the torque. So he's saying the first case he has given the armature current as 10 amperes. And the second case, he is asking us to calculate the torque when the armature current is reduced to 5 amperes. So for that, particularly, we need to calculate the back EMF. We know that back EMF is nothing but the supply voltage minus the drop which is occurring across the armature. So using this particular equation, we calculate the back EMF as V minus, that is the supply voltage 200 volts minus the armature current when it is 10 amperes multiplied by the resistance of the armature, we get it as 180 volts. And same the back EMF when the current is 5 amperes, we got it as 190. So we know that from EB is equals to 5 ZNP by 60A. EB is directly proportional to the speed. So we know that the mechanical power developed is nothing but TA into omega. So he's asking us to calculate the torque developed by the motor. So for this, we have EB1 and EB2 divided by N1 by N2. We already have the speed as N1 as 2000 by N2. From this, EB1 is 180 volts divided by 190. From this, we can calculate the N2 value. We will first get the speed value. So we know that mechanical power is nothing but 2 pi nt by 60. So this 2 pi n by 60 is nothing but your omega. So now we got the speed N2. This is nothing but the speed when the armature is drawing 5 amperes of current. So we got N2 here. We know that for calculating the torque equation, we have equated the mechanical powers developed across the armature. So now I am going to equate EB into IA, which is TA into omega. So now he is asking us to calculate the torque when the armature is drawing 5 amperes of current. So we have the equation for torque as 0.159 into 5 into P into Z by A into IA. We know that the current here is drawn by the armature is 5 amperes. And flux is not given in the question, so we need to calculate the flux. Number of poles, so number of poles is given as, we are not given the information about the number of poles. Conductors information is also not given. So for this particular case, we need to calculate EB into IA, torque into omega. EB, we got it as 190 volts. IA is 5 amperes. Torque is like this, and this is 2 pi into, we got the speed from the previous calculations of EB1 and EB2, which is nothing but N2 is equals to EB1 by EB2 into N1, which is nothing but 180 by 190 into 2000. So whatever the value of N2 we get here will be substituted here. N2 value will be substituted here. Upon substituting, we can get the equation for torque as 190 into 5 divided by 2 pi into N2. So this is the torque which is developed by the motor across the armature. This is how we calculate the torque when the back EMFs, when the different values of armature currents are given for a particular motor, separately excited motor. Moving on to the next numerical, we have wave connected 8 pole 60 kilowatts 300 volts DC generator. Number of conductors are given as 540 and it delivers the load current. If the brush shift, that is nothing but the theta, is 4 degrees, is asking us to calculate the demagnetizing and cross magnetizing ampere turns per pole. So we already have the demagnetizing ampere turns per pole as theta m by 360 into Z into I, and cross magnetizing ampere turns, which we have seen under the topic of armature reaction, which is nothing but Zi 1 by 2p minus theta m by 360. So these are the two relations which we use to calculate the demagnetizing ampere turns per pole and the cross magnetizing ampere turns per pole. So theta m, which is given as 4 degrees, number of conductors are given as 540, and we have to calculate the current. So now here we are considering the wave connected generator as a constant flux machine. So that's why now I am taking my armature current value. So we have to first calculate this current value which is required. So this current value is nothing but the current in each conductor. To calculate the current in each conductor, we first need to know the armature current. So to calculate the armature current, we have the power, which is given as 60 kilowatts. We know the power relation P is equals to V into I. I is nothing but 60 into 10 cube divided by the voltage is given as 300. So from this, we get our IA value as 200. So this is the total armature current. So now we need to calculate the current in each conductor. So to calculate the current in each conductor, we divide the armature current by the number of parallel paths. So as it is wave connected, we know that the number of parallel paths is always 2. So now the current in for each conductor is given as 100 amps. We got the current as 100 amps. Now we are going to substitute it in the relations for demagnetizing ampere turns, that is nothing but Zi into theta m by 360. Z is nothing but, from the previous, it is 540. I is nothing but 100 amperes, which we have got in the previous slide. Theta m is 4 degrees, which is given in the question, divided by 360. Upon calculating this numerical value, you are going to get the number of demagnetizing ampere turns required to neutralize the demagnetizing effect in the armature reaction. Then we have to calculate the cross magnetizing ampere turns using the relation Z into I 1 by 2p minus theta m by 360. Z is given as 540, the current is 100 amperes, number of poles is 8, theta m is given as 4 degrees divided by 360. Upon further calculating it, we get the number of cross magnetizing ampere turns required to neutralize the cross magnetizing effect under the armature reaction for a DC generator. So this is how we calculate demagnetizing ampere turns and cross magnetizing ampere turns required to neutralize the armature reaction effect in a DC generator. Moving on to the next numerical. A 4-pole 32 conductors lap wound DC shunt generator. So shunt generator, we know that shunt field winding is connected in parallel with the armature, which is again connected to the load. This is a shunt field winding, armature winding, armature current. shunt current, and the load current, which is delivered by the armature. Number of poles 4, conductors 32. Lap wound machine, number of parallel paths is equals to number of poles, which is nothing but 4 again. The terminal voltage across the load is given as 200, delivering the 12 amperes of current. So now this is taken as IL, which is equals to 12 amperes. We have armature resistance as 2 ohms. Shunt resistance as 200 ohms, which is driven at a speed of 1000 rpm. Now he is asking us to calculate flux per pole in the machine. To calculate the flux per pole in the machine, we have Eg, which is nothing but 5 ZNP by 60A. So we need to calculate flux here. Before that, we need to calculate Eg value. So to calculate Eg value for a shunt machine, Eg is equals to V plus Ia Ra. Terminal voltage is 200. We also need to calculate Ia now. So Ia is equals to IL plus ISH. ISH is again VSH or V terminal divided by RSH. So VSH is nothing but 200 volts divided by RSH is given as 200 ohms. So now my ISH will be 1 ampere. From this, I have 12 amperes as my line current and 1 ampere as my shunt field current. So my armature current will now be 13 amperes. So we have armature current as 13 amperes and RA is 200 plus 26, which is nothing but 226 volts. So we got our Eg value. Substituting in this, Z is 32, N is 1000, number of poles 4, 60, number of parallel paths 4. So we get the flux value here from this equation. So this is how we calculate the flux here. Then in this next case, he has asked, the machine is now run as motor with the same terminal voltage, drawing 5 amperes of current from the main lines and maintaining the same magnetic field. So he is asking us to find out the speed of the machine. So now let us analyze when the same machine is running as motor. So when the same machine is running, let us consider DC shunt motor now. In the question, he is saying that if the machine has to be run as motor with same terminal voltage is now 200. Taking this 200 volts here, shunt resistance and the armature resistance being the same, 202. This is 2 ohms, 200 ohms. And now it is drawing 5 amperes from the main supply lines. So now your IL value will be 5 amperes. We have to calculate IA and ISH first. So ISH is again, as it is a shunt machine, we know that the voltage is common for all the parallel branches. So we have 200 volts of terminal voltage divided by the shunt field resistance. We get it as 1 ampere. we know that supply line current is equals to IA plus ISH. From this, we derive the IA value as 5 amperes of IA, that is IL minus 1 ampere. So we get it as 4 amperes. So now your armature current is 4 amperes. So maintaining the same magnetic field, he is now asking us to find out the speed of the motor. So to find out the speed of the motor, we require our EB. EB is again 5ZNP by 60A. We need to calculate EB for our motor now. So to calculate EB, we are going to write it as V minus IA RA. For this particular branch, to calculate EB across the armature. So V is given as 200. We got IA as 4 and armature resistance is 2. 200 minus 8. So here now your EB will be 192 volts. As we got EB value, substituting this in this particular equation, we are going to derive, that is 192 volts is equals to 5. We have calculated it from this previous case, assume it as X. So we got the value of 5 as X. Number of conductors is 32. He's asking us to find the speed. Number of poles is 4 divided by number of parallel paths. X is already known from the previous case, which we have calculated the flux in the previous case when the machine is running as generator. So substituting the same value of flux in this equation, we get the speed. So this is how we calculate the speed of the same machine when running as generator as well as motor. Moving on to the next numerical. We have a 4-pole series motor. So we have seen so far about the separately excited generator, compound generator and shunt motor. So now we are seeing it for the series motor. So series motor, we have number of poles as 4 and the conductors are 944. We know that when conductors are wave connected, number of parallel paths will always be 2. And flux is given as 34.6 millivebers. He has also given the total mechanical torque as 209 Newton meters. He is asking us to calculate the line current taken by the motor and the speed at which the applied voltage is 500. So total resistance of the motor is given as 3 ohms. First, let us draw the series motor diagram or the circuit. We know that the field winding and the armature winding both will be connected in series for a series motor. So this is a series motor, series field winding and the armature field winding, EB and the applied voltage. So now he's saying the total resistance. So total resistance can now be taken as RA plus RSE. This value he has given as 3 ohms. So the applied voltage is 500 volts. He is asking us to calculate IL, the line current which is delivered to the motor armature circuit. And also he is asking us to find out the speed at which it will run for applied voltage of 500. He is asking us to find out the speed also. So the given data for us in the question is torque, the resistance. So for a motor, EB is equals to V minus IA into RA plus RSC. So EB can also be found out by the equation 5ZN P by 60A. So as we are not aware about the speed and the back EMF, so now we are going to calculate First our armature line current, then we are going to calculate the armature current. So here in series motor, as all the field winding, armature winding and the supply lines are in series, so we can take IL is equals to ISE is equals to, let me consider it as one single current I. So now he has also given the torque for us in the question. The value of torque is given. So from this I can calculate my IA. So torque equation, it is nothing but 0.159 into 5 Z by A into P into IA. So from this, the value of torque is given as 209. 209 is equals to 0.159 into flux per pole is given as 34.6 milliwebers multiplied by the number of conductors 944. Number of poles is given as 4 multiplied by IA. And this number of conductors is divided by number of parallel paths. As it is wave connected, it is 2. So from this, we will get the value of IA. Let us assume we got the value of IA as X amperes. So now our IA value is X amperes. So we know that IA is equals to IL, which is equals to ISC. So now we got it as X amperes from the previous case. So now he is asking us to find out the speed. To calculate the speed, we need to first write on the back EMF, which is nothing but V into IA RA plus RSC for a series motor. So V he has given us 500, IA we got it as X and this is 3. From this we will get the EB value in volts. From the EB equation, that is nothing but 5ZNP by 60A. We are going to calculate the speed value as EB into 60A divided by 5ZP. Substituting, let us consider this value as let us consider this value as Y. Substituting Y here, 60 into number of parallel paths is 2 as it is wave connected, and flux is given as 36.2 milliwebers, number of conductors 944, number of poles 4. So we get the speed of the motor in RPM. So this is how we calculate the speed at different terminal voltages or different applied voltages for a DC series motor. For a series motor, we have the resistance is the sum of the armature resistance and series resistance as they are connected in series, and we also observed that a single current will be flowing from the supply lines through the armature, through the series field winding and also through the supply. So this is how we calculate the speed or anything asked in the question for a particular DC series motor. Moving on to the next numerical. A armature winding of 4 poles. Number of poles are 4 here and voltage is 250 volts. Shunt motor. So shunt motor, let us draw the circuit for the shunt motor. We know that field winding is in parallel to the armature winding in a shunt motor, which is supplied by a DC source. This DC source value is 250 volts. Number of poles are 4 and it is lap connected. We know that parallel paths for a lap connected winding is equals to the number of poles. So we can write simply the parallel paths in this particular kind of motor is nothing but 4. And he has given 120 slots, each slot containing 8 conductors. So the number of conductors in all the slots will be 120 into 8, which can be 960. Number of conductors will now be 960, and he has given the flux as 20 milliwebers. And the current taken by the motor, which is nothing but 25 amperes. The resistance of armature and field windings. The resistance of armature is 0.1 and this is 125 ohms. He has given the constant losses, that is nothing but rotational losses, is 810 watts. So all these are given in the question. He is asking us to find out the gross torque and the efficiency. We know that the equation for the torque is nothing but omega. Let us again equate the mechanical powers for calculating. So now your mechanical power is nothing but omega into torque, which is again equal to EB into IA. So he is asking us to calculate the armature torque. So we can calculate the armature torque from this equation, that is EB into IA by omega. Case 1. And he is also asking us to calculate the efficiency. He has given the constant losses. Now we need to find the input and output power and the torque for this particular case. So to calculate the torque, we require first EB and then we also require IA. So to calculate IA, we know that the line current is already given as 25 amps. We need to calculate the shunt field current. So to calculate the shunt field current, we have the voltage 250 divided by 125, which is nothing but 2 amperes. So for the motor, we know that line current is equals to armature current plus shunt field current. So from this, armature current will now be 25 minus 2, which is nothing but 23 amperes. So we got the armature current value here. So case 1, to calculate armature torque, we have the equation as EB into IA by omega. So we got IA value as 23 amperes. Then we need to find out EB now for the shunt motor. So EB for shunt motor can be written as V minus IA RA. So V is given as 250 volts, IA is 23 into RA 0.1. 250 minus 2.3. We got EB value here. Then substituting it here, TA is equals to into IA 23 divided by omega, which is nothing but 2 pi n by 60. So we were not given the speed in the question, so we need to calculate the speed as well. phi ZNP by 60A. We got our EB value as 247.7. Flux value is given as 20 milliwebers. Number of conductors are given as, we got it as 960. We need to calculate the speed. Number of poles are 4. Into 4. From this, we will get the speed value as some x RPM. Substituting this speed value here, x divided by 60. We get our armature torque, which is nothing but 247.7 into 23 into 60 divided by 2 pi into the speed which we have derived here from the EB equation. So with this we found our armature torque. From this he is asking us to find out the efficiency. Efficiency is nothing but output power by input power into 100. So output power, we have input power as, the output power as EB into IA, that is mechanical power, divided by input power VI. So EB into IA, EB we have got it as 47.7 into 23 divided by V. V is nothing but the terminal voltage, or this one, 50, and the line current is 25 amperes. Here we are going to add the losses which are given in the question, the rotational losses, which is given as 810 watts, the input power V into I, that is nothing but 25 amps into 250, which when multiplied by 100 will give you the efficiency of the this is how we calculate. We know that EB into IA is the mechanical power which is developed at the armature, and V into IA is the electrical input or the electrical power which is supplied to the motor. This is how we calculate efficiency and the losses calculations for DC shunt motor. So in this lecture we have covered different numericals on the torque equation. Then we have covered the numericals on how to calculate the speed for different separately excited motor. Then we have calculated the cross magnetizing and demagnetizing ampere turns required to neutralize the armature reaction effect. Then we have calculated the numericals for the same DC machine running as generator and motor for different values of armature current. Then we have calculated the line current for the motor for DC series motor. So we have covered the 3 types of motors: compound motor, series motor and shunt motor. Then we have calculated the efficiency calculations and gross torque based by calculating the armature torque which is developed across the armature for shunt motor. So these are the numericals on DC motors, various numericals on DC motors for different mathematical expressions which we have derived in our previous classes for the DC motors. Thank you.